All right, let's dive into something pretty fundamental. Light, but not just the simple stuff. We're going deep. We'll be using an awesome video from QuantumFracture called Ya en serio, ¿qué es la luz? That translates to, seriously, what is light? This channel is great at breaking down complex physics, making it understandable and fun. We all know light is important, but have you ever stopped to think what light actually is? We'll see that the more we learn about light, the weirder it gets.
Yeah, it's a wild ride. It all starts with Isaac Newton, a pretty smart guy, but even he had some things wrong about light.
Oh yeah, I remember learning about this. Newton thought light was made of particles, right? Tiny little bullets of light.
Exactly. You imagine these tiny particles just streaming through space. This makes sense to him, especially when he was messing around with prisms.
Yeah, prisms split white light into all those colors like a rainbow. How did Newton use that to back up his particle theory?
Well, he thought each color was a different type of particle, and these particles had different masses. He figured the heavier particles, like red light, wouldn't bend as much when passing through a prism, while lighter particles, like violet light, would bend more.
Huh, that's pretty clever.
Yeah.
But it wasn't the whole story, right? What happened?
Well, some other scientists came along in the 18th and 19th centuries and started doing some experiments that really challenged Newton's model.
What kind of experiments?
They were shining light through tiny holes, expecting the light to go through in a narrow beam, like those tiny bullets Newton talked about.
Yeah, that makes sense. If it's a stream of particles, a smaller hole should make a smaller beam.
Right, but that's not what they saw at all. The light actually spread out after going through the hole. It's called diffraction, and it's something that waves do, not particles.
So does that mean light is actually a wave?
That's what they started to think.
Yeah.
And then came the double slit experiment, which basically sealed the deal on the wave theory.
Oh yeah, the double slit experiment. Light goes through two slits and you get a pattern of bright and dark bands.
Exactly. It's called an interference pattern, and it's like the fingerprint of wave behavior. Think of what happens when two waves in water meet. They can either make each other bigger or they cancel each other out. The same thing happens with light waves in the double slit experiment.
Okay, so case closed, light is a wave, end of story. Right.
If only. It gets much weirder. In the early 20th century, quantum mechanics came along and threw a wrench in everything. Scientists were doing experiments with super low light, where they could actually count individual particles of light. These are called photons.
Wait a minute, hold on. Particles of light. I thought we just figured out light is a wave.
I know, it's mind-blowing. Some experiments show light acting like a wave, like diffraction and interference. And then other experiments show light acting like a particle.
So which one is it? Wave or particle?
According to quantum mechanics, it's both.
Both. All right. My brain is ready to be bent. Tell me more about this wave-particle duality.
All right, so picture a single photon traveling from a light source to a detector. You'd think it would just go in a straight line, right?
Yeah, like a little bullet.
Nope. Quantum mechanics says that the photon doesn't just take one path. It takes all possible paths at the same time.
All possible paths, so it's not just going straight, it's also like looping around and zigzagging all at the same time.
Yep, you got it. It's exploring every single route, and then somehow all these paths combine to determine where it ends up.
That's crazy. So how do all those paths end up making what we actually see? It can't just be random, right?
It's definitely not random. Each path has something called an amplitude. Think of it like a rotating arrow, kind of like the hand on a clock. And get this, the probability of finding the photon at a particular spot depends on adding up the amplitudes for every path that goes to that spot.
Adding up rotating arrows? Okay, that sounds pretty out there.
I know, it's weird, but it works. You see, some paths, they reinforce each other, making it more likely for the photon to end up there. And other paths, they interfere and cancel each other out.
So the photon is taking all these crazy paths, but the way they combine determines where it's most likely to show up.
Exactly. And this is why we usually see light going in straight lines. The straight paths all reinforce each other. But when light has to go through small openings, like in the double slit experiment, then the other paths start to matter, and you get those wave-like interference patterns.
All right, I think I'm starting to get it, but it's definitely some mind-bending stuff. So light can be a wave and a particle. Are there any other quantum surprises in store for us?
You bet there are. Have you ever heard of the Hanbury Brown and Twiss effect?
I don't think so. What's that all about?
So we take two detectors, and we point them at the same light source. You'd think the detectors would just click randomly as photons hit them, but they often click together. It's like the photons are synced up.
Hold on, that's even weirder than all those paths. Are you saying these photons are secretly communicating with each other or something?
It's not quite communication, but it's definitely strange. The crazy thing is, this effect is easy to explain if you think of light as a wave. Actually, that's how Hanbury Brown and Twiss first discovered it, using radio waves. But when you try to explain it with individual photons, it gets really tricky.
Okay, so what does quantum mechanics say about it? How can these photons act so coordinated?
It all comes down to this mind-boggling thing in quantum mechanics.
Yeah.
Particles being indistinguishable. Let me give you an example. Imagine trying to track two electrons.
Okay, so you've got electron 1 and electron 2.
Well, here's the thing. Electrons don't follow neat, predictable paths. They're constantly jumping around. So you can't really keep track of which electron is which.
So our technology just isn't good enough to keep up with them.
It's not just that. At the most fundamental level, there's no such thing as electron 1 and electron 2. They're just two electrons, and they're completely interchangeable.
Okay, now my brain is really hurting. So you're saying those labels, electron 1 and electron 2, are totally meaningless.
Exactly. It's not that we can't tell them apart. They truly are the same. And you know what? The same thing goes for photons. They're indistinguishable too.
Okay, so how does this indistinguishable thing explain those synchronized clicks in the Hanbury Brown and Twiss effect?
Because we can't treat their paths as if they're independent. This creates some correlations in how they behave, making them arrive at the detectors in a way that looks like wave interference. It's almost like their indistinguishability creates this weird quantum link between them.
Wow, this is heavy stuff. But at least this quantum weirdness explains some pretty awesome things like lasers.
We got it. The fact that photons are indistinguishable is crucial for how lasers work. In a laser, all the photons are emitted with the same properties, same energy, same direction, same polarization. This creates that super focused single color beam that makes lasers so powerful.
So it's like a super organized team of indistinguishable photons all doing the same thing.
That's a great way to put it. This wouldn't be possible if photons weren't indistinguishable.
All right, so we've covered light as a wave, light as a particle, and now this mind-bending indistinguishability thing. Is there anything else we need to know to really understand light?
Well, there's one more layer to this. Quantum field theory.
Quantum field theory. Okay, here we go. Even deeper down the rabbit hole.
In quantum field theory, we don't think of photons as individual particles anymore. We think of them as excitations of a field, the electromagnetic field. Imagine this field like a giant ocean, and photons are like ripples or waves in that ocean.
So instead of tiny bullets, we have ripples in a giant ocean of energy.
Got it. It's a different way of thinking about it, but it helps us understand how light interacts with matter in other fields. This field idea also helps explain how particles can be created and destroyed.
Okay, I'm going to need a minute to process all of that. But before we do, remember that photon packer thing they mentioned in the video? It seemed like it could have some cool uses.
Yeah, that's a great example of how scientists are using these weird quantum ideas to create new technology. This photon packer could really change the game for multiphoton microscopy, which is used to image living tissues without damaging them. It basically creates bundles of photons. This ensures they all hit a target molecule at the same time, making multiphoton absorption much more efficient.
That's pretty wild. So we're talking about manipulating light at the quantum level to understand biology and develop new medical tech.
It really shows how powerful this deep dive into light can be. What starts as a simple question leads us to explore the most fundamental parts of physics and uncover the mysteries of the quantum world.
Speaking of mysteries, we've only just scratched the surface of quantum optics.
Exactly. There's so much cutting-edge research and potential applications that we haven't even touched on yet.
This is definitely something we'll have to come back to. But for now, let's jump into the exciting world of quantum optics research in part 2 of our deep dive. Stay tuned.
All right, welcome back to our deep dive into light. We just finished talking about how light can be a wave and a particle at the same time, and how those particles, photons, are all fundamentally indistinguishable. It's a lot to wrap your head around, but it leads to some really interesting phenomena like the Hanbury Brown and Twiss effect, right?
Exactly. That's where things get even weirder. Imagine we have two detectors, and they're both pointed at the same light source. Now, you might think that since photons are emitted randomly, the detectors would just click at random times too.
Yeah, that seems logical.
But here's the thing. The detectors often click in sync. It's almost as if the photons are coordinating with each other, even though they're emitted randomly.
Wait, hold on. That's crazy. Are you saying they have some kind of secret communication system? Not exactly communication, but it's definitely strange. The funny thing is, this effect is easy to explain if you think of light as just a wave. In fact, that's how Hanbury Brown and Twiss first observed it, using radio waves. But when you try to explain it with individual photons, it gets really tricky.
So what does quantum mechanics have to say about it? How can these independent photons act so synchronized?
It all boils down to another one of those mind-boggling quantum concepts, the indistinguishability of fundamental particles.
We were just talking about that with electrons.
Right. Remember how we said there's no such thing as electron 1 and electron 2, just two indistinguishable electrons?
Yeah, it blew my mind a little.
Well, it's the same with photons. They're fundamentally indistinguishable, so you can't really tell them apart.
Okay, I'm following so far, but how does that indistinguishability explain those synchronized clicks in the Hanbury Brown and Twiss effect?
Because of the indistinguishability, we can't think of the photons' paths as totally separate events. This leads to some subtle correlations in their behavior. It's like their indistinguishability creates a sort of quantum connection between them, causing those synchronized clicks.
Wow, quantum mechanics is really messing with my understanding of reality.
I know, it's wild.
But hey, at least this quantum weirdness explains some pretty cool stuff, like lasers, right?
Absolutely. The fact that photons are indistinguishable is key for how lasers work.
So if they weren't indistinguishable, lasers wouldn't be possible.
Exactly. In a laser, all the photons are emitted with the same properties, the same energy, same direction, even the same polarization.
So it's like a super organized army of photons all marching in perfect step.
Exactly. And this leads to that super focused, single color beam of light that we all know and love.
Okay, so we've got light as a wave, light as a particle, and this whole indistinguishability thing. Is there anything else we need to consider to really grasp what light is?
There's one more layer to this quantum onion. Quantum field theory.
Oh boy, quantum field theory, that sounds intense.
It is, but it gives us an even deeper perspective on light. In quantum field theory, we stop thinking about photons as individual particles. Instead, we think of them as excitations of a field, the electromagnetic field.
Excitations of a field. Okay, break that down for me.
Imagine this field as a vast, invisible ocean.
Okay, I'm picturing it.
Now imagine photons as ripples or waves moving through that ocean.
So instead of those tiny bullets, we have ripples in a giant ocean of energy.
Precisely. It's a different way of thinking about it, but it's incredibly powerful.
How so?
Well, this field-based view helps us understand how light interacts with matter and other fields in a much deeper way. It also sheds light on how particles, like photons, can be created and destroyed.
Created and destroyed? That's even weirder than everything else we've talked about.
I know, it's mind-blowing, but it's a fundamental concept in quantum field theory.
Okay, I'm definitely going to need some time to digest all of this.
It takes time, but it's worth the effort.
It definitely seems like it. Before we move on, remember that photon packer idea they mentioned in the video? It sounded like it had some pretty cool potential.
You're right, that concept is a great example of how scientists are harnessing the strangeness of quantum mechanics to create groundbreaking new technologies.
So what exactly is this photon packer and what could it be used for?
Well, it's a theoretical device that could revolutionize a technique called multiphoton microscopy, which is used to image living tissues without damaging them. It essentially creates bundles of photons, ensuring they hit a target molecule at the same time. This would make multiphoton absorption much more efficient, leading to clearer images and potentially new applications in fields like medicine.
So we're talking about manipulating light at the quantum level to improve our understanding of biology and develop new medical technologies. That's incredible.
It really highlights the power of this deep dive into light. What starts as a simple question can lead us to explore the frontiers of physics and uncover the mysteries of the quantum world.
Speaking of unraveling mysteries, we've only scratched the surface of what's happening in the field of quantum optics.
Exactly. There's a whole universe of cutting-edge research and potential applications that we haven't even touched on.
This is definitely a topic we'll have to revisit in the future. But for now, let's dive into some of the most exciting breakthroughs in quantum optics research. Welcome to the final part of our deep dive. All right, welcome back to our final part of this deep dive on light. We've gone from Newton's particle theory to the wave-particle duality. We've even explored the bizarre world of indistinguishable photons. But hold on tight, because in this last part, we're going to the cutting edge of quantum optics research. We're going to see how scientists are using the quantum weirdness of light to create some mind-blowing technologies.
It's seriously an exciting time to be working in this field. It feels like we're explorers, charting new territory. With each new discovery, we unlock more possibilities for innovation.
Okay, I'm ready for some more quantum amazement. What's some of the groundbreaking research that's going on right now?
One area that's really captivating is the development of single photon sources.
Single photon sources? What are those? What makes them so special?
Picture this, a device that can emit light, one photon at a time. That kind of control is crucial for so many quantum technologies, especially quantum communication and quantum computing.
Yeah, I can see how that would be important. If you're building a quantum computer that relies on those super delicate quantum states of individual photons, you definitely don't want a bunch of extra photons messing things up.
Exactly. Single photon sources are also really important for quantum cryptography. That's where we use quantum mechanics to create those unbreakable encryption codes.
Oh, wow, unbreakable codes. So we could be using light to create those super secure communication channels. That sounds like something straight out of a spy movie.
It does, but thanks to all these advances in quantum optics, it's becoming a reality.
Okay, so how do you actually make a single photon source? Is it like a super tiny laser pointer that just shoots out one photon at a time?
Not quite a laser pointer, but you're on the right track. One way we do it is by using tiny imperfections in materials, like diamonds.
Imperfections in a diamond. That doesn't sound very high tech.
I know, right? But it works. These imperfections, they're called nitrogen vacancy centers. They have this special quantum property that lets them emit photons one at a time when you hit them with a laser.
So we're using imperfections to make the most precise light sources imaginable. That's pretty amazing.
It is, and researchers are always coming up with new and innovative ways to make and control single photons. It's such a dynamic field, full of potential.
Okay, so besides these single photon sources, what other breakthroughs in quantum optics have you excited?
Another area that's really taking off is quantum sensors.
Quantum sensors, huh? What are those?
Think of sensors that are so sensitive they can pick up on the tiniest changes in their environment, like little fluctuations in magnetic fields or even gravitational waves.
Wow, that sounds incredibly powerful. What could we do with sensors like that?
The possibilities are endless. They could completely change medical imaging. Imagine being able to see inside the human body with incredible detail, but without any invasive procedures.
So we could diagnose diseases much earlier and with greater accuracy.
Exactly. And that's just one example. Quantum sensors could also make navigation systems way more precise. We could create incredibly accurate clocks, even help locate resources underground.
It's like we're giving ourselves superpowers.
It's not far off to say that quantum sensors could transform the way we see and interact with the world.
This whole deep dive into light has been an incredible journey. We started with basic ideas and ended up exploring the frontiers of quantum research. It's amazing to think that something as simple as light can lead to such a profound scientific discoveries and technological breakthroughs.
I couldn't agree more. Light is so much more than just something that lets us see. It's a fundamental part of reality, and its quantum properties are opening up new possibilities that were once thought to be impossible.
So as we wrap up this deep dive, what's the main thing you want our listeners to remember?
I want them to come away feeling a sense of awe and excitement about the quantum world. The more we learn about light, the more we realize just how much more there is to discover. We're at the beginning of a quantum revolution, and the future is full of possibilities.
I love it. So to all our listeners, keep exploring, keep learning, and keep asking questions. The world of quantum optics is full of mysteries just waiting to be uncovered. Thanks for joining us on this illuminating journey into the nature of light. We'll see you next time for another fascinating exploration.